All right, so 14.3 is probability of compound events. We're going to spend 2 days on this, so I consider it a little bit more difficult than your average lesson. Let's talk about a few of these. Of course, I'm missing an important pen. Here we go. All right, so we're going to look at the probability of independent events. And what that means is the outcome of one event does not, in capital letters, double underline, the outcome of one event does not affect the outcome of the other events. So remember, an event would be like rolling a die, spinning a spinner, picking something out of a hat. Those are different separate events. And so your notation for probability of independent events looks like this. So the probability of A and B. It's important that this word "and" is there. So I might say the probability of flipping a coin and spinning a spinner is. Or, flipping a coin and getting heads and spinning a spinner and getting an even number. Whatever it might be. That's what it's going to look like. And what you're going to end up doing is taking the probability of the first event and you're going to multiply it to the probability of the second event. Or however many events there happens to be, you're going to multiply each of those probabilities together. So here's some examples of independent events. So they might say, find the probability of rolling a 4 on a number cube. And spinning the color red. So here's your important word "and." And is separating those separate events. So one event is rolling a 4. The other event is spinning the color red. So you'd find each of those separate probabilities and multiply them together. Another example might be selecting something out of a bag or a hat or whatever it might be, a box, whatever, with replacement. And that's the important part. So let's say I'm selecting marbles out of a bag, because you had that on one of your homeworks the other day. Cam, are you even writing anything down, or are you just playing with a calculator? Yeah, you've missed a whole bunch of stuff. So, for instance, you had selecting marbles out of a bag on your homework previously. So if I want to know the probability of selecting a white marble and then a black marble, those are different events. So when I select the white marble, I'm going to assume I selected the white marble, but then I put the white marble back in the bag, because that means that if I don't put it back in the bag, it's going to affect my overall probability. Remember, probability is favorable over total. And if I have 10 marbles in the bag, and I have 3 white marbles in that bag, what's the probability of selecting a white marble out of that bag? 10 white marbles, 10 total marbles. I'm sorry, 3 white marbles, 10 total marbles. What's the probability? 3 out of 10. If I take that white marble, and we assume that we picked out a white marble on the first draw, and I set it aside, and I want to know the probability of selecting a black marble, and let's say that there's 2 black marbles in the bag also. What's my probability now? I set the white marble aside. What's the probability now of selecting a black marble? You've got 2 of them in the bag.
2 seconds.
2 out of what?
4.
How many marbles are in the bag right now? 9. So me setting that white marble aside affected the overall total probability, didn't it? Because you now have 2 out of 9 rather than 2 out of 10. If I put the white marble back in, the probability would be 2 out of 10. They would be considered independent because their bottom numbers are the same. So I don't want, for an independent event, one event to affect the other. All right, so look at example 1. So Roberta is flying from Birmingham to Chicago to visit Grandma. What a good girl. She has to fly through Houston to get there. The airline reports that the flight from Birmingham to Houston has a 50% on-time record, and the flight from Houston to Chicago has a 90% on-time record. What is the probability that both flights together will be on time? So if we had to write it out in probability shorthand, we would be writing probability of Birmingham to Houston and Houston to Chicago. We want a probability that both flights will be on time. So according to what we did above, we're going to find the probability of being on time from Birmingham to Houston. I'm going to multiply it. Everybody should be writing, unless you have ESP, which I don't think any of you do. Uh-huh. Times the probability of the Houston to Chicago flight of being on time. Now, they actually gave us those probabilities, didn't they? So the Birmingham-Houston flight has a 50% on-time ratio. Do I put 50 in here? No, what do I put in? What's the decimal equivalency of 50%? 0.50, right? And I'm going to multiply that to, I also gave you the Houston to Chicago on-time percent, which is 90%. So what are you going to put in for that? 0.90. And if I multiply those together, 9 times 5 is what? 45. And if you ignore your zeros on the end, I had a total number of decimal places of 2. So it's really 0.45 or what? We have a 45% chance that she will get to Grandma on time. So what's holding her back? Which one? Birmingham to Houston, right? Alabama.
Where's Houston?
Texas.
Where's Chicago?
Great state of Texas. Seriously, you don't know where Chicago is? Please tell me that's not true. All right. So let's, Tristan, let's look at the probability of dependent events. So one of your jobs today is going to determine, is this an independent situation or a dependent situation? So for dependent, the outcome of one event affects the outcome of the other event or events. So we've already kind of talked about some of these, but here's an example of a dependent event where we are selecting without replacement. So without is the key word. In other words, without those marbles in the bag. Before, if I put the marble back in the bag, remember I had 3 white marbles and 2 black marbles in a bag of 10 marbles. So if I wanted to select a white marble and then a black marble, my probability, if I replace the marble once I select it, with replacement was 3 out of 10 times and then 2 out of 10. But here, assuming I have a white marble the first time, I'd still get 3 out of 10 for the first white marble, but now there's 9 marbles in the bag because I'm not putting it back in. So now I have a probability of selecting a black marble of 2 out of 9. So it will affect the second event if we don't put that item back in the bag, the box, the hat, whatever it might be. It could be a deck of cards. I could be drawing out a card and putting it back in, then drawing out a second card and putting it back in. So let's write that one down. Drawing 2 cards. Each draw is considered a separate event. One at a time. Bless you. And the reason why I'm writing one at a time, remember yesterday you were dealt 5 cards or 10 cards, you want to know the probability of that, or how many outcomes that there could be, it's going to make a difference, because this time we're finding probability, not the total number of combinations or permutations. So one at a time from a deck of cards. And not capital double underline replacing them. So there again we have the no replacement. So I don't draw a card and put it back in the deck and draw another card and put it back in the deck. I draw a card and I keep it out. So your notation, your general notation for this would be the probability of A and B. And again, that and is an important word. You're going to see later that that word is going to change to an or, and it's going to change how we calculate that probability. And we still do the probability of the first event times the probability of the second event. Well, let's add on to that. Not just the probability of the second event, but the probability. I'm going to get rid of mine. The probability of the second event following A. So I have to consider that this is following that one and it's actually occurring. Yes?
What do you recommend if this is like...
It's not actually multiplication. It doesn't mean P times A. It's probability of event A. Kind of like our f of x, our function notation. Like a subscript. They whoever made it up just didn't do it that way. So this is what's generally followed. Okay, so flip your paper. Let's look at an example of a dependent event. So example 2, at the school carnival, so go back to elementary school days, winners in the ring toss game are randomly given a prize from a bag that contains 4 sunglasses, 6 hairbrushes, and 5 keychains. Very exciting. 3 prizes are randomly drawn from the bag and not replaced. So there's the important word. The fact that it's not replaced means that it's dependent events. So you have to find each probability. So how many total items are in the prize bag? 4 sunglasses, 6 hairbrushes, and 5 keychains. How many total? So there's 15 total items. It's important to note that we know how many items are in there. So what's the probability first that I'm going to draw out some sunglasses?
15.
There's 4 favorable sunglasses, right? Out of 15 total items in the bag. So I have 4 out of 15. I'm going to multiply that to the probability of a hairbrush, but I'm not replacing it, which is good because if I pull out a pair of sunglasses and I give it to the kid and I say, oh no, wait a minute, we need to take that back. Do you think they'd be upset? They'd start crying, for the most part, or they'd kick me in the shins, one of the two. They wouldn't be happy. So we pull it out and give it to them, right? So what's the probability of a hairbrush? How many hairbrushes are there now currently in the bag? 6 hairbrushes. Out of how many total items now in the bag? 14 items now in the bag because we lost one, right? How many keychains? There are 5 keychains because we haven't drawn any out, right? Out of how many items now in the bag? Because we now have a pair of sunglasses and a hairbrush that's outside the bag, so we now have 13. So don't just go ahead and multiply across and multiply across. If you can reduce, I want you to reduce. So can't I reduce? I can either reduce vertically here with a 2 or diagonally here with a 2, right? So I choose to divide the 4 by 2 and the 14 by 2 and I get 7. Can't I also cancel the 5 with the 15? Or I can cancel a 3 with the 15 and the 6. I can cancel this far away from each other as long as I have one numerator and one denominator. I'm going to get rid of the 5, so 5 goes in there 1 time and in here 3 times. Can I cancel any more? I can cancel the 3 to the 6. So 3 into 3 once and into 6 twice. Is there anything left? I can't cancel horizontally, so you can't cancel those. So then multiply straight across, and we have 2 times 2 times 1 is 4 over 1 times 7 times 13. What's 7 times 13? 91. So I have a 4 in 91 chance of getting that combination sunglass, hairbrush, keychain. Now, mind you, I am not just grabbing 3 things out of the bag. I'm drawing them one at a time. The fact that I'm drawing them one at a time affects the probabilities because one is dependent upon the other. All right, look at the second one. We have a whole new bag of 15 items with the same things in there. So I've refreshed my bag. What's the probability of selecting a hairbrush? 6 hairbrushes out of 15 total times. So I give a hairbrush away. I want to pick a second hairbrush. How many hairbrushes are now in the bag? Because I gave one away, so instead of 6, there's now 5 hairbrushes, right? And how many items in the bag? 14 times how many keychains? 5 keychains out of 13. So now cross cancel. I'm going to cancel a 2 into the 6 and the 14. A 5 into the 15. It doesn't matter which 5, but only one of them. And then I can cancel these 3s. Anything else? Nope. So I have 1 times 5, which is 5. And then 7 times 13 again, which is 91. Which has a higher probability of occurring? The hairbrush keychain. Then we have this word not. We have this word not. So we need to know what do we do when we have this not in our probability. So let's go ahead and go through everything again. I've refreshed my bag back to my original items. What's the probability of selecting sunglasses? First time. 4 out of 15 times. Then I get a hairbrush. How many hairbrushes? 6 out of 14. So far it's no different than A, right? But it says this basically not a keychain. The kid's sitting there staring at me. Please, anything but a keychain. Anything but a keychain. So how many keychains are currently in the bag?
1,
There's 5. How many items are currently in the bag? 13. So out of 13 items, 5 of them are keychains. So how many are not a keychain? What's 13 minus 5? 8, right? So don't we have 8 items that are not a keychain out of 13 total items? Question?
Yeah, how do you know, like, if there's like a string of questions like this, how do you know that it starts over at 15?
We'll make that assumption that it does. If it doesn't, then they would tell you, but make the assumption that it does start over. That's a new situation. If we had this situation with that bag, what would we have? Let's see what this situation would be with that same bag. So assume that we're just analyzing different probabilities.
If it was like a carnival, so kids were in a line, you'd have less each time the kids come out.
That's right, but we're just assuming we're having 3 kids. We're analyzing the probability that would occur every time I give out something for 3 separate times. It's a possibility that somebody's coming along and giving me stuff to refresh my bag every so often. So, unless it's specifically said that you have the bag that you're left with, and it won't say that. Assume that your bag's refreshed. Okay, so cross cancel. I'm going to cancel 2 into the 4 and the 14. And I'm going to cancel a 3 with the 15 and the 6. Is there anything else? Nothing. What's 2 times 2? 4. 4 times 8? 32. And then 5 times 7 is 35, so then you're going to have to multiply 35 times 13, which I would assume you'd use your handy-dandy calculator, and you get 455. The only way that you can compare this probability to those is you would have to convert all 3 of them to their decimal equivalencies and compare the decimals. All right, so then let's talk about, so we've talked about independent events, dependent events. Now we're going to talk about something called mutually exclusive. So mutually exclusive would be events that cannot occur at the same time. for instance, I might say to you, what's the probability that I'll draw a card that is an ace or a queen? Can I draw a card that's both an ace and a queen? No, there's no such card. So those are mutually exclusive events. I want one or the other, but I don't want one. So one thing that you need to understand is that for mutually exclusive and mutually inclusive, that this is one event, not two. I'm going to draw a card that's either an ace or a queen. So what's now changed in how I'm saying that?
Oh,
I'm using the word
or.
right? So or implies that this or that's going to happen, but not both. So it implies you have one event. So an example that you can write down would be the probability of rolling a 2, or there's that keyword 4 on a die. Can you roll both a 2 and a 4 at the same time on a number cube, on a die? Yes or no? No? So you might want to put in here that these cannot occur at the same time. Does that look fuzzy to you, or is it just me? Is it fuzzy or clear? Oh, it's just me? Okay, good to know. All right, so let's look at example 3. Alfred is going to the Sonoran Desert Animal Shelter to pick a new pet. Today, the shelter has 8 dogs, 7 cats, and 5 iguanas available for adoption. In my household, if he came home with the iguana, he'd be taking it back. Just saying. If Alfred randomly picks an animal to adopt, what is the probability that the animal would be a cat or a dog because it's my household? I don't want the iguana. So I'm going to write that probability as probability of a cat, or there's a keyword dog. So we are going to find the probability of the cat and add to that. So this time we are not multiplying anymore. So if you have one event, we no longer multiply the probabilities together. We're going to add the probabilities together. And the probability of selecting a dog. So what is the probability that it would be a cat? First of all, how many total animals are there to choose from? So we've got 7 plus 5 is 12, plus 8 is what? So 20 animals total. Right? So how many favorable for cats? 7 out of 20, plus how many favorable for dogs? 8 dogs out of 20. See how they have the same denominator? Can't I just add them? 7 plus 8 is 15 out of 20, but I can reduce that, right? What goes into 15 and 20? So 5 goes in here 3 times, and 5 goes in here 4 times. So I have a 3 in 4 chance, or a 75% chance, that Alfred's coming home with a cat or a dog. Actually, in my household, it better be 100%, because otherwise I'm taking it back. Yes?
I just realized something on the question up there. Like, would it matter if, like, the order the personality in? Like, instead of putting
No. Yes. You mean these ones above here?
Yeah.
Yes, order matters. Because it could change, especially order would matter on, well, I don't know, I'd have to look. Because keychain would be 5 over 15. But your hairbrush would be the same. It probably would still work out the same. I don't think so. I don't think it would matter. No, you'd have different fractions. But overall, you'd have the same denominators. That wouldn't change. And you would have the same numerators. And you're multiplying everything. Does it matter what order you multiply in? No. So it shouldn't make a difference. Okay, so probability of inclusive events. So mutually exclusive versus mutually inclusive. So these, of course, would be events that can occur at the same time. So we talked about the deck of cards one. Let's see if I can get this up higher. So a really good example comes from drawing cards out of a standard deck. The probability of drawing an ace or, and this is key that I'm saying or and not and, of drawing an ace or a spade. Can an ace also be a spade?
Yeah.
Yes. How many ace of spades are there? One. So I want the probability of drawing an ace or a spade, but what I'm implying here is that I don't want it to be both an ace and a spade. It's one or the other from a deck of cards. And then put here in parentheses, it is possible to draw a card that is both. So our probability for inclusive events would be probability of A or B. So here's that important word, or. So again, we're still going to be adding our probabilities together. So it looks really similar. The probability of the first event plus the probability of the second event. So in this case, the probability of drawing an ace would be what? How many aces in a deck of cards? 4 out of 52. Plus the probability of drawing a spade. How many spades? How many? 13 out of 52. But then I have to subtract the probability of A and B occurring at the same time. I don't want them both to occur at the same time, so I don't want an ace of spades. How many ace of spades are there? 1 out of how many? 52. So I would have 4 out of 52 plus 13 out of 52 minus 1 out of 52. So there's a difference between inclusive and exclusive. I have to take away when they occur at the same time. So last page, last example. A dog has just given birth to a litter of 9 puppies. There are 3 brown females, 2 brown males, 1 mixed color female, and 3 mixed colored males. How many puppies altogether? 9 puppies total, right? You didn't have to count them.
14. Oh,
Do they add up to 9?
I
Okay.
was counting the 9.
Oh, okay. If you choose a puppy at random from the litter, what is the probability that the puppy will be male or mixed color? Can a male also be mixed color? Okay, so we want to take away that we don't want a male mixed color. Either male, no matter what color, or a mixed color, no matter male or female. But I don't want a male mixed color. I'm weird. Go figure. So our probability would be probability of male or mixed color equals, I want to find the probability of male plus the probability of mixed color and subtract out the probability of male and mixed color. I'll just make it MC. And then we'll look at it a different way and I'll show you that it still works. Alright, so what's the probability of the puppy being male? How many male puppies? So there are 3 brown females, 2 brown males, so there's 2, female and 3, so 2 and 3. What's that? So we have 5 males out of how many total puppies? 9. Plus, how many are just mixed color? Yeah, I have 1 mixed color female and 3 mixed color males. So 1 and 3 is 4 mixed color puppies out of the whole kitten caboodle, right? But then I need to take away puppies that are both male and mixed color. So how many male mixed colored puppies are there? 3 mixed colored males. So I want to take away 3 out of 9 puppies. They're all the same denominator. Don't try to reduce any of these fractions because then you're going to have to get LCDs anyway. So what's 5 plus 4? 9 minus 3. 6 out of 9, it does not reduce. 3 goes into both, you get 2/3. So I have a 2 in 3 chance, or 67%, that I'm going to choose a male or a mixed color. Now go back and look. Aren't there 6 puppies that are either male or mixed colored but not both? If you go back and count, so you could have done it that way as well. All right, any questions?